This video is sponsored by Brilliant.
Today we're going to look at an interesting algebra known as the split octonions. And we're mostly looking at this because there's this really interesting, what I'll call a mutant matrix representation of this algebra, which I never thought I would see, but it's actually been around for a while. Okay, so let's see what these split octonions are. So they're an 8-dimensional vector space over the real numbers. So we've got a basis given by the number 1, which is like the multiplicative identity, and then these E1s through E7s. So that means everything is of the form A plus B1 times E1 added all the way up to B7 times E7, where A and the BI are real numbers. And then these basis vectors satisfy the following multiplication rules. So like I said, the number 1 is the multiplicative identity, and then E1 squared, E2 squared, and E3 squared are all -1, whereas E4 squared, E5 squared, E6 squared, and E7 squared are all +1. So the fact that these are +1 instead of -1 make them the split octonions instead of just the octonions. And then the rest of the multiplication is described by the following diagram. And so how does one read this diagram? Well, if you go in the direction of the arrows, you pick up a plus sign, and whatever's next in the line tells you the product. So for instance, E2 times E5 is E7 because we went in the direction of the arrows, whereas E7 times E5 is -E2 because we went opposite the arrows. Furthermore, all of these are considered to be loops. So for instance, E5 times E4 is equal to E1. So that arrow should have started at E1. So let's fix that. And that's because E5 times E4 loops back around to E1. And furthermore, like E5 times E6 is -E3 because that's going in the opposite direction. Okay, so now we've got an idea of what the multiplication looks like and why this differs from the regular octonions, but it's still non-associative like the regular octonions, and we can show this really easily. Let's look at E1 times E2 times E4. So by the diagram, E1 times E2 is E3, so this is E3 times E4. But then E3 times E4 is -E7 because we're looping around opposite direction of the arrows. So that's -E7. But now let's look at this associated the other way. So E1 times E2 E4. So let's see, E2 E4, well that's going in the opposite direction and it's looping back around to -E6. So this is E1 times -E6. In other words, it's -E1 times E6. But let's look at E1 times E6. Well, that's looping in the opposite direction as well, back to E7. So that cancels the minus sign that we have here and just gives us +E7. So that means that these two are not equal, giving an example of the non-associativity. Now, in the regular octonions, everything has a multiplicative inverse. But that's not true in the split octonions. And there are in fact 0 divisors that don't have multiplicative inverses here. So I'm going to prove that we've got a 0 divisor. I won't check that there's no multiplicative inverse though. I'll leave that for you. So for instance, we could take 1 plus E4 times 1 minus E4. And note that if we multiply that out, we'll end up with 1 minus E4 squared, but E4 squared is simply 1, so we get 1 minus 1 is 0. So that's what it means to be a 0 divisor. You take two things that are non-zero, you multiply them together and you get 0. So this is not something that happens in, for instance, the non-split octonions, like I said, or the quaternions, or the complex numbers, or the real numbers, so on and so forth. Okay, so that's a little bit about the arithmetic of the split octonions, but what we really want to look at is the so-called Zorn representation, or Zorn's representation of this algebra.
If you're looking for a free and easy way to learn more about calculus and linear algebra, check out today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. Keep your love for learning alive with Brilliant's interactive lessons, perfect for those ages 10 through 110. Let me show you what sets Brilliant apart. Their interactive courses are designed to make learning fun and engaging. From math to science to data analysis and computer science, Brilliant offers a wide range of topics that'll have you saying, I never knew learning could be this exciting. What really makes Brilliant shine is its problem-solving approach. You won't just passively absorb information, you'll actively learn through hands-on interactive lessons that challenge your thinking and creativity. Brilliant is available on your phone, tablet, or computer, and Brilliant will support you every step of the way. No matter what skill level you're at, Brilliant can help you improve. Not sure where to start? How about with the topic of this video? They have introductory courses in calculus and linear algebra. And if you don't need that, they have a variety of STEM topics: physics, computer science, abstract algebra, and more. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial, and the first 200 people will get 20% off their annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So often when you're in a linear algebra class and you're first learning about matrices, so arrays of numbers, someone might ask the question, well, is there ever an array of things that are different? Like maybe some of the entries are numbers and some of the entries are vectors, or some are numbers and some are matrices, so on and so forth. And generally, at least one person in the class asks this kind of question. And in the past, I would have said there's no use for such a thing. But in fact, there is a use for such a thing, and it's Zorn's matrix vector representation of the split octonions. And it's given by the following setup. We first consider the following matrix vector, or maybe mutant matrix. And so notice the diagonal is just made up by numbers. So we've got a real number A and a real number B. But the off diagonal is made up of vectors. So we've got a three-dimensional vector here and a three-dimensional vector here. And then between matrix vectors like this, we define the following product. So here we've got a matrix vector, here we've got a matrix vector, and the product is defined to be as follows. So it's somewhat technical. So notice we've got here A1 times A2 plus the dot product of V1 and W2. Recall that the dot product of vectors produces a scalar, so that makes sense. And then in this entry, we've got the scalar product of A1 and V2 plus B2 and V1, so that gives us a vector. And then plus the cross product of W1 and W2, which also gives us a vector. So that's good, that puts a vector in that entry. And then we've got a similar object down here. Notice we've got A2W1 plus B1W2 minus the cross product of V1 and V2. And then finally, we've got something over here in the bottom right that looks pretty similar to this thing in the upper left. That produces a number or a scalar. Okay, so it turns out that this object or this structure is isomorphic, in other words, the same as the split octonions. But in order to see that, we needed to know how to map between these two spaces, and here's how you do it. So if you take a split octonion A plus B1E1 all the way up to B7E7, that corresponds to the matrix vector defined like this. So we've got A plus B4, A minus B4. Those are your numbers on the diagonal. And then here we've got a vector made up of B1 plus B5, B2 plus B6, and B3 plus B7. And then a pretty similar vector down here, but the coefficients of B1, B2, and B3 are now negative. So we've got negative B1 plus B5, and then so on and so forth. So it turns out that this kind of mapping with this product is exactly the same as the multiplication outlined by this diagram inside of the split octonions. Okay, so let's do a couple of examples of this happening. Okay, so we're going to start off with a very simple example. So let's start with this E1 times E6. So by the diagram, what is that? Well, let's look. We go E1 times E6, that'll be negative E7. So here, like I said, we have negative E7. But now let's map E1 into that matrix vector representation. So that's going to be mapped like this. So we'll have 0, and then here we'll have the vector 1, 0, 0. Down here the vector -1, 0, 0. And here the scalar 0. So that's based off of that map that we had earlier. And then what about E6? So E6 gets mapped down to the following matrix vector. So it'll be 0, 0, 1, 0. And then we've got a 0, 1, 0 as well. And then a 0 here. Okay, nice. But from here, we need to do that operation just to make sure we get what would correspond to negative E7. So let's see. Well, in this upper left entry, we're going to have something like this. So it'll be 0 plus the dot product of 1, 0, 0 and 0, 1, 0. So of course that's going to be 0, but I want to put all the structure in here just to start. And then we'll have 0 times 0, 1, 0 plus, next up will be 1, 0, 0, and then we'll have plus the cross product of two things. So that'll be -1, 0, 0 cross 0, 1, 0. Okay, nice. So that's that upper left entry. Okay, well now let's look at this lower right entry. Or sorry, that's the upper right entry. Now let's look at the lower left entry. So we'll have 0 multiplied into -1, 0, 0. And then that'll be plus 0 multiplied into 0, 1, 0, and then minus the cross product of those two. So that'll be 1, 0, 0 cross 0, 1, 0. Okay, nice. And then in our lower right entry, we'll have 0 plus the dot product of 0, 1, 0 with -1, 0, 0. Okay, so that's it all said and done. But now let's do some calculations. So like I said before, this is kind of obviously equal to 0 because that dot product is 0. Then this down here is kind of obviously equal to 0 as well. Furthermore, a large portion of this is equal to 0, so I'll just cross it out. And that only leaves us the need to do the cross product of those. But it's pretty easy to check that the cross product of these two vectors is simply the vector 0, 0, -1. So you can check it out on your own with the standard way of doing the cross product. Similarly, the cross product of this is 0, 0, 1, but we've got a minus sign out front. So now putting this all together, we're going to get the following matrix vector. So we've got an entry of 0 here, and then 0, 0, -1, and then another 0, 0, -1, and then 0. But let's notice that that corresponds to -E7, just as we wanted it to. Okay, so it works for this simple example. Now let's look for a little more complex example. Okay, so for our next example, we're going to look at the product of the following two octonions. We have 3 plus E1 plus 2E3, and 2 plus E2 plus 4E5. Okay, so let's just maybe distribute all the things that we need to, and then maybe use this diagram as motivation for the necessary products. So we're going to start with 3 times 2, which is 6, plus 3 times E2, which is 3E2, and then plus 3 times 4E5, which is 12E5. So that's everything multiplied by this first term. Now we'll do E1. So E1 times 2 is 2E1. E1 times E2 is E3, which we can see from the diagram over here. E1 times E5, let's see that. E1 times E5 is E4. So that's going to give us plus 4E4. Okay, good. And now let's do 2E3 times 2, so that'll give us 4E3. So we have 4E3. And then let's see, E3 times E2, well let's see, that's going in the opposite direction, so that'll be minus E1, but that's attached to a 2, so that'll be minus 2E1. And then finally E3 times E5, well what's that? Okay, E3 times E5, so that loops back here to negative E6. So in the end we'll have minus 8E6. Okay, good. But there's one thing that cancels, and that would be this 2e1 and this negative 2e1. And then after that, maybe it's just useful to put this kind of in order. So putting this in order, we have 6 plus 3e2. And then we're gonna have 5e3. And that's from, let's see, this e3 term here and this 4e3. So like I said, plus 5e3. And then we've got 4e4, so that's going to be plus 4e4. And then we've got a 12e5, so 12e5 minus 8e6. Okay, so that's the number all sorted like in the kind of correct order. Okay, so now let's turn these two octonions into those matrix vectors. So this first one looks like this. So we'll have 3 and then 1, 0, 2. So that's, using that rule that we described earlier. And then here we'll have negative 1, 0, negative 2, and then a 3 right here. And let's do some color coding. So let's maybe underline this one in green and underline this matrix vector in green too, so that we know where it's coming from. And then let's see here. Here we'll have 2. And then next in this entry, we will have 4, 1, 0. Okay, and then let's see, down here we will have 4, negative 1, 0. So we don't pick up a minus sign in the 4 because it's the coefficient of E5. And then finally in this entry we will have a 2. And then let's do some more color coding. So let's underline this in blue and this in blue as well, just to show that where those two things came from. Okay, great. So now let's write out all of this necessary calculation and maybe we'll speed through this. Okay, so there we have it. That's putting these two matrix vectors together using that crazy product that we had. And then from here, we just need to finish off the calculation. So let's maybe note that this dot product is pretty clearly equal to 4. This dot product is pretty clearly equal to negative 4. And then we'd have to calculate those cross products as well. So I'll just jump to the final matrix vector and you can see that it is the following object. So it's 10, and then we'll have 12, negative 5, and then a 5 here. And then in this lower left entry, we'll have the vector 12, negative 11, negative 5. And then here we'll have 2. But now let's make sure that that makes sense. Let's recall that this upper left entry was the sum of the real part and the coefficient of E4. So look, 6 plus 4 is 10. And then this lower right was the difference. 6 minus 4 is 2. So that works out. And then this was the coefficient of E1 plus the coefficient of E5. But that's going to be 0 plus 12, so that's how we get this here. And then likewise, we get something similar here. And then let's recall that this second entry of this vector was the coefficient of E2 plus the coefficient of E6. So let's see, 3 minus 8 is negative 5. And then that's how we get here too, but it's negative the coefficient of E2. So negative 3 minus 8 is negative 11. And then similarly, we get a negative 5 here and a 5 here, and that works out. Okay, so in the end, we see that all of these correspondences make sense. So let's maybe underline this in magenta just to mention that that octonion corresponds to this matrix vector. So of course, that doesn't prove that we have an isomorphism, but it at least gives evidence towards having an isomorphism. So maybe I should have said this earlier, but maybe I'll leave it as a question. So why do we need this crazy matrix vector representation of an octonion instead of just a normal matrix representation like we do with the quaternions and the split quaternions and the complex numbers and the split complex numbers? Why can't we have one for the split octonions or the octonions for that matter? So maybe post in the comments your answer. And if you're still around and you haven't subscribed yet, maybe consider subscribing. It really helps us out, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.